Okay, so let's continue where we left off. We were looking at the y component of the electric field, so we get dx sine of theta over r squared, and the sine of theta is y over x squared plus y squared, opposite over hypotenuse. And so therefore, the y component looks like k lambda times, we can actually pull the y out, and when we replace the sine of theta, we have a y that's a constant because we're integrating an x, and so we just get dx over x squared plus y squared, again to the 3/2. So now we can do our integrals. Let's see. We actually need to do some substitutions, so it's a little bit tricky. So p equals, say, x squared plus y squared to the 1/2. And x is therefore p squared minus y squared to the 1/2. And we can replace dx with dp. Dx becomes p squared minus y squared to the minus 1/2 p dp. And so our integral for the x component, x over x squared plus y squared to the 3/2 in dx becomes the integral of p to the minus 2 in dp. The result of that is minus 1 over p, which in terms of x and y is minus 1 over x squared plus y squared to the 1/2. And so the x component of the electric field ends up being minus k times the charge density times 1 over, well, we have to evaluate it at x1 to x2. Let's just, one is minus infinity and the other is infinity, but let's just leave them as x2 squared plus y squared to the 1/2 minus 1 over x1 squared plus y squared to the 1/2. And basically what we see is that because x2 equals infinity and x1 is equal to minus infinity, and they both get squared, what really matters here is just 1 over x, because the y is negligible when x is infinity, and so we get 1 over x is basically what we get. So we get 1 over infinity minus 1 over infinity, and therefore the x component is 0. And so it must be true that only the y component remains. And for the y component, we want to use, an integral. We have dx over 1 plus x squared to the 3/2. We can use that integral. We have to do some manipulation to get our integral into that form, so it's a lot of work when you're integrating the electric field by brute force. Let's see, what do we get? Let's push this up a little bit, and our y component, ey, ends up being k times lambda, we get y squared, and we get x over 1 plus x squared over y squared to the 1/2. And this gets evaluated from x1 to x2, where one is minus infinity and the other one is plus infinity. And that gives us k lambda over y times x2 over x2 squared plus y squared to the 1/2, or square root, minus x1 over x1 squared plus y squared square root. And of course, again, x1 is equal to minus infinity and x2 is equal to infinity. And that gets us to, let's see, EY ends up being K times the charge density over Y times, let's see, the difference here is in these two terms, this is positive infinity and this is negative infinity, but we have minus a negative infinity. So we actually get, and then we have infinity underneath and infinity here underneath, so we get 1 plus 1, or it's really 1 minus minus 1. And so the y component is 2 times lambda over y. Sorry, I have the k there as well. And so the electric field is really, so if this is the infinitely long line of charge, the electric field at some point is only pointing in that direction. There's an EY component only, and there's no x component. So we will eventually get to a place where we will be able to solve this kind of charge distribution, or the electric field produced by this kind of charge distribution, in a much simpler way using Gauss's law. But this is just the brute force approach.